also wrote a paper.
Huh? Okay. Oh,
yeah, but like we're just partying loud for what? Yeah, from 11 to 3. There's like 5 checks. Yeah, but like I'm just gonna say that. Yeah. Yeah.
oh gosh. Okay. I'm sorry for the late start, y'all. I just mismanaged my time. Let's see. Sarah B. Claire. Matt. Luke. Jaden. Emma. Yep. No, is Emma? Oh, there's Emma. Okay. Yeah. So she usually sits there. And, yeah. I was like, wait a minute, that's not the back of her head. Liza. Stewart. Yeah. Ethan. Manya. Olivia. Kashal. Diego. Darwin. Sean. Jules. Doa. Yep. Matthew. Colin. Emily. Yep. Rennick. Sarah T. McKenna. Okay, sorry for the late start. So here's where we were last time. Well, here's what we were talking about last time. We were talking about triple integrals. And reminder, here's the sort of the big picture overview of triple integrals. There are lots of circumstances where you want to do what I, as you all know, like to call a chop it up, add it up strategy, right? So maybe you want to compute the mass of a three-dimensional solid where density varies in all 3 directions, right? And double integral it doesn't work, right? But if you chop it in 3 directions, make a 3-index Riemann sum, which we call a triple integral, works fine. So likewise for various other applications. Okay, so you can turn applications into triple integrals. Conveniently, it is also true that we can turn triple integrals into iterated integrals. And now that is the argument of why that works is something we can't really do in this class, but it's a lot like double integrals, just, 4-dimensional. Right? We can't make that argument. There's a perfectly good algebraic argument, again, a little bit beyond what we can do in this class. And then that said, once you have an iterated integral, it's all over but the shouting. You just have to crank with the fundamental theorem a few times. Okay, so that's our big picture strategy. Again, final reminder, well, probably not, but reminder, don't try to just immediately turn, a 3-dimensional mass into an iterated integral. As a process, that the argument doesn't really make sense by itself because the square peg round hole, the units don't work out, you might say casually. You need this in some sense for the units to work out, for the argument to actually be meaningful. And then you can say, and by the way, that turns into an iterated integral. Okay. The slicing process. Well, again, kind of not that different from double integrals. We slice, find the bounds by looking at the first and last slices, then fix it and move on to the next variable. Right? And so what does that look like geometrically? Well, it's something like this. We won't go through all that again like we did last time. What we're going to spend most of today on, what we're going to spend most of the, gosh, it's probably going to be most of today, but is examples of this process in action that we've already discussed in sort of the abstract. Okay. All right. And remember, last thing before we get our hands dirty, if you want to find bounds, they correspond to certain points. You want to identify those points. If you want to understand a point, that point's going to be on a surface or various surfaces. Perhaps you want to identify those surfaces. Those surfaces, of course, you understand them with equations. So there's this kind of connect the dots to the bounds connecting to certain equations, which you can then solve to find said bounds. Okay, and we did this example last time. Let me just hit some highlights on this. How did we find our upper bound for X? You know, where'd that come from? Well, it's here's what X slices look like, and here's the last one. What do I know about this point? Well, I know three things about it. I know it's on that plane, and I know it's on this plane, and I know it's on this plane. So how am I going to understand that upper bound? How am I going to understand this point? Well, by solving these equations, and that gives me that upper bound. Then you fix the slice, repeat the process, etc. Okay. All right. Yeah, we've already talked about not slicing through corners, just like with double integrals. You want to think about what's naturally a function of what, and think strategically on that. And if you don't want to solve for a certain variable, don't put it on the inside where you would need to solve for it, right? So things like that. And then we had to absolutely rush through this this next point of strategy here. And this is this idea of projection. So I think this is best understood by example. But what I mean by a good projection is one where the shadow, in other words, the projection itself, is a desirable shape. Some shapes are better than others for slicing purposes. There needs to be a clear top surface and a clear sort of bottom surface. And what I mean by clear is that it needs to be consistent across the projection. I'll show you an example. And with those being the case, looking at the projection will actually give you the same bounds as if you hadn't looked at the projection. So let's see an example so this all makes sense. We're going to look at a region, the region in the first octant, right? So we're going to look just sort of in the near, X, Y, and Z are all non-negative. Bounded by these two surfaces, Z equals 1, and this paraboloid, which like that. And if you look at how these intersect and look at the part in the first octant, you get this solid here, which is a real artistic challenge to draw, by the way. And by the way, I'm going to go ahead and give you another plug. If you want to know all of the sort of tips and tricks of how I was able to draw this thing, watch my videos, right? This exact solid is one of the examples that I go through in great detail in those YouTube videos and miscellaneous topics playlist, and it's called Drawing 1 and Drawing 2. So anyway, for your consideration. Okay, so how are we going to slice up this solid? The first thing I want to observe is even without looking at the picture, I look at this equation And I pretty handily notice I would rather solve for z than either of x or y, because I don't like square roots. So if I can possibly avoid putting, if I can possibly make z the inside variable, I definitely want to do that, right? Because otherwise there's going to be square roots, and square roots are bad. Okay. So this suggests using this order of slicing. Again, dz, the one I want to solve for being the variable on the inside. Okay. Okay, so now I claim that there is a and we can slice it up the old-fashioned way, but I claim that there's a good projection into the XY plane. Now let me go through what I mean by good projection. We've already described it, but now let me show you the picture. What does a good projection look like? Okay, our solid here. If you project down into the XY plane, the shadow, the projection itself looks like that. And I suppose there's better areas and worse areas. Rectangles, I guess, would be the goal. That's the ideal. That's the dream, right? But so you're not going to get any rectangular shadows of this particular shape. So that being said, this isn't bad. It's a reasonable projection. Okay. But furthermore, another importantly nice thing about this projection is if I ask myself then, okay, well, if I were to look at a point in this projection, and let's pretend that I already know my x bounds and my y bounds, and so x and y are fixed. And if I just want to know, okay, but then for that x, for that y, what's the range of values of z? Well, here's the relevant slice, and this point that defines the lower bound is always on that surface. If there's a single surface that always tells me where my lower bound is. That's nice. It will not always be the case. Sometimes, depending on which way you're projecting, you might have, well, sometimes it's this surface, sometimes it's that surface, and that's bad. Okay. And then likewise, the upper bound for z is always going to come from that point, which is always on this surface. So this is again, I'm going to call it a good projection because the projection itself isn't horrible. The lower bound is consistently on one surface. The upper bound is consistently on another surface. Yeah.
Why do we need the projection if we could just find the points of intersection?
Yeah. No, it's not a matter of need. This isn't a you have to, this is a you get to situation. So I claim that what's going to work out is that if we take this projection point of view, which I haven't finished describing yet, right? Then it's going to end up being easier. Yeah, it's going to be, this is a good thing. Okay, so we have on the one hand, a motivation for how to slice, and we could just go through and kind of do it manually, and we can talk through that. But we can also make the projection argument. And here's the big idea of the projection argument. Think about this slicing process in the first place. And I'm doing dy on the outside here. So y slices, what do y slices look like? Well, they're kind of like this. Right, and we have a first and a last, etc. Generic slice looking like this. Okay, what do y slices of the projection look like? Well, y slices of the projection look like that. In particular, notice that if I were to look at a slice and then project it, what I get is a slice of the projection. It's almost a semantical game, right? But the projection of the slice is a slice of the projection. So it's an observation that's the hard thing about the observation is that it's so clear. But every time you slice up the solid, you are simultaneously slicing up the projection. So the punchline is the range of values that you're going to get for y, the range of values that you're going to get by actually slicing up the solid is the exact same range of values that you would get instead by just slicing the projection. And which would you rather draw? Yeah, I mean, pretty clearly, right? I mean, it's much easier to draw that projection. It's so two-dimensional for one thing. That's really nice. By the way, it's again, no mean feat to draw these slices and to draw the solid in the first place. It's tricky. So big advantage then. And furthermore, let's look at a single Y slice now then. There's an actual Y slice. Here's the Y corresponding Y slice of my projection. What do X slices look like? Going in the X direction now. Well, my X slices up here are like that. What do my X slices look like down here? Well, I'm just kind of cruising along down here. The first X slice on the solid, the first X slice on the projection, same. Ditto the last X slice on the solid corresponds to, well, again, no surprise, the last Y slice. X slice on my projection. So for both the X and the Y bounds, because we're doing XY on the outside, the bounds that I would get by looking at the solid are exactly the same as the bounds that I would get by looking at the projection. And it's so much easier to do. So in particular, this projection down here, this projection is pretty easy to understand. All I really need to understand is where this edge is, which of course comes from where those surfaces intersect, which is easy to see as a circle, simple equation. And with that known, I can pretty much immediately write down my X and Y bounds kind of together, right? Because I know, sorry, I did this in the wrong color. My X and Y bounds, looking at this projection, X and Y bounds are that. Because it's a two-dimensional, it's just a quarter disk, and I have the equation, and we've been doing double integrals forever. So the artistic challenge of drawing the solid and drawing the slices and thinking about no. Just look at the projection. Slice up the projection. We're 2/3 of the way done with this problem already. Everybody see what happened there? Okay, so furthermore, the Z bounds are not going to be that much trouble either. And again, we've kind of already observed this, that if I look at some point down here in this projection, X and Y being fixed, because after all, I do know my X and Y bounds. When I'm trying to find my Z bounds, X and Y are now fixed. Okay, so with X and Y fixed, my lower bound for Z is going to come from that point, which is always on that surface, which has that equation, which gives me that for the lower bound. And my upper bound is going to come from that point, which is on that surface, which has that equation and gives me that upper bound. So I think that's a much easier argument to make than trying to draw the slices and thinking about, okay, well, which point on the three-dimensional solid, which surfaces is that on, and in some sense doing a big three-dimensional challenge. The projection argument much more convenient. Let me pause there for questions. How do y'all feel about that? Does this satisfy your concern?
Yeah.
Okay.
It makes sense now.
Okay. Cool. Yeah. All right. Okay. So yeah. Neat way to go. Here's another example. I'm going to do this one both ways. I'm going to do this one the old fashioned way. We're going to slice it up. And then I'm going to make a projection argument after to see how much easier that is. Okay, so starting with, oh, by the way, I'm arbitrarily doing my slicing in this order. Really makes no difference in this case. For the record, by the way, it absolutely makes a difference in this case, right? I mean, we had a strong preference to put Z on the inside. So sometimes the order of the slicing really matters. Here, balls are highly symmetric and, it's going to be annoying either way. So pick the least annoying, I suppose. Okay. All right. So artistically, Okay, so starting with X, for no particular reason. Well, X slices kind of look like that, right? That's a slice perpendicular to the X axis. The first X slice is back there where I'm going to say it's kind of a freebie, that's -1 because this is a unit ball. The last slice is going to be right there. And again, kind of a freebie, -1. Okay. Okay, now we fix a value of X. So we're going to focus our attention now on this X slice, which, by the way, kind of hard to draw. This, drawing a circular slice cross section of a sphere. It's just, I don't know, it's harder than it looks. I think it came across not horrible in what I drew here, but that took me a little while to kind of get I don't know, to make it not just look terrible. So don't underestimate that challenge. And to make things easier, I'm going to come over here and look just at the slice itself. This gets the sphere out of the way and makes for the picture a little bit easier to analyze, because I don't really care about the rest of the sphere at this point anyway. Right? We just care about, at that value of X. Okay, so our next question is, what is the range of values of Z? So what do Z slices look like? What happens when I take horizontal, perpendicular to the Z axis? What happens when I take these Z slices of my X slice? Again, don't care about what's happening up there or down here, not my problem. We will get there. We will get them with different values of X, right? But I want to know the Z bounds as a function of X, not overall. Okay, so on this X slice, Z slices start there, kind of proceed along, and then end there. Everybody see my picture? Okay. All right. Now, what can I say about those points? What do I know about those points? Let's see here. Those points. What do I know about those points? Well, I know what X is. So I know X is X. And these points here, this, like the upper bound here in particular, for example, that point, it's really kind of, oh, missed. Try it again. It's kind of here. It's on my sphere. So I should write this down. So I know what X is. I know it's on the sphere. And let's see now, what else do I know about that point? I can't make any claim to knowing Y being fixed or something like that, because Y, we haven't even gotten to Y yet, so I can't claim prior knowledge to Y. But in fact, I actually do know something about Y. And the thing I like about this example is it shows how sometimes the information that you need is something you have to see from the picture. You just got to see it from the picture. This point that I'm looking for, describing my maximum value of Z, the picture tells me, the symmetries of the sphere tell me that point has actually Y equals 0. And I picture, right? Got to have the picture. Okay, so with all of that said, We then need to solve for, well, let's see, what are we solving for? Z. We need to solve for Z in this equation. So solve for Z, and what you get is these two values, as it turns out. And of course, we're looking at the upper bound, so we take the positive one. You get identical algebra if you're looking at the lower bound, same algebra, pick the lower one, pick the negative one. How are we doing? Everybody see how that works? Okay, and this slice it up approach is, again, kind of annoying for this one. And again, there's good news coming. The projection approach is going to crush this problem much more easily. But we've got our X slice fixed. So X is fixed. We're now going to fix Z. Fix some value of Z. My Z slice of my X slice is that right there. Now on that Z slice of that X slice, looking only at that Z slice of that X slice, Y starts at that point and ends at that point. And again, the process repeats. What do I know about the points? Well, these points are on the sphere, and the sphere has a certain equation, and X and Y are both already known, and solve, and you get this. And of course, they are, as they are allowed to be, functions of X and Z, which are, of course, fixed. Okay, how are we doing? Is everybody with me? All right, now let's take the much more desirable projection point of view on this now. By the way, you can project in any direction you want on this. Again, spheres are highly symmetric, but just to be consistent with what I've got on the page here, I'm going to project in the XZ direction. The projection of this sphere into the XZ plane is, well, it's a disk. How do I slice up a disk? Well, we've done that a million times before back in when we were dealing with double integrals. And the way you slice up a disk is that right there. We're 2/3 done, and all we've done is kind of, look at the picture and flashback to, wait a second, what happened? How do I deal with a double integral? Isn't that better? When you can, when there is a good projection. It's awesome. Yeah, and of course, now we do have to finish then. So let's see here. So for a given value of X and Z, looking at, in other words, at a particular Y, Z slice of an X slice, in other words, looking at what I've got in the Y direction, this starting point is on the back hemisphere, right? Solve for Y in the equation of the sphere. The front point up here is on the front hemisphere. Solve for Y in the equation of the sphere. So it's just so much faster. It's way more convenient if you can do a projection, if the rules are satisfied. Y'all feel good about this one? All right. Okay, now this is a tricky one. And this is a good drawing exercise as well. I've got a solid that's bounded by 5 planes. And just from an artistic point of view, if I were to just give you 5 random planes, oh my gosh, the brutality, right, of having to draw 5 random angled planes, what kind of weird shape do you get? Oh my gosh, it'd be too hard, right? So there is a foot in the door here that won't always happen in life, but make the problem tractable enough to actually be reasonable in a class like this, right? And the trick to notice here is that there are 3 equations in which there are no y's present. And if you think about it, if there's no y's present in those equations, then you can change y all you want. It doesn't affect whether the equation worked. And what the punchline is, those surfaces have to be parallel to the y-axis. And now this is a really good thing to always keep your eyes open for. If you see equations where there are certain variables just not present, then you know something useful there. So these are all parallel to the y-axis. If I want to draw something that's parallel to the y-axis, all I really have to do is kind of, draw what it looks like in the xz plane, and then I could just drag parallel to the y-axis. So for example, let's see here, let me do it like this. Z equals 0 is that in the xz plane. Z equals x is that in the xz plane. And x plus z equals 2 is, well, something kind of like that in the xz plane. I can fairly quickly see I really only need these parts of these three curves. And so now knowing that all of these are actually surfaces that are parallel to the y-axis, okay, well, they're parallel to the y-axis, so just take this and just drag parallel to the y-axis. So we've got 3 of the 5 surfaces now, I'm going to say understood. They're not drawn perfectly, but we see what's going on with 3 of these 5 surfaces just from that one observation. Okay, and then it's kind of all over with the shouting at this point. Let's see what remains is I've got y equals 0. Okay, well, y equals 0 is gonna, the way y equals 0 slices up this prism is like that, right? Here's the plane y equals 0. How does that vertical plane y equals 0, how does it cut through this Toblerone bar? It makes a triangular cross section like that. And then the one that is a little bit sort of artistically challenging is this one here. This is it's an angled plane. It's kind of angled in all 3 directions. It's kind of, if you will, its normal vector is kind of coming out of the screen at us. And oh gosh, let's see if I can you might initially draw by representing it as, this is a triangular sort of slice that it would take of the first octant. And so how does this slice through the Toblerone bar? It's going to have a slice, I don't know, so kind of like that. And if you really don't trust yourself to see that geometrically, you can just kind of plot some points. I mean, after all, where these purple lines are. You can just take the X and Z for these purple lines, plug in and see how far the Y goes over. You can see how far does it go over there and there and there. Anyway, I claim it ends up looking something like this. Okay, so it's tricky to draw, but again, some clever observations makes it kind of doable. Okay, so let's get to slicing it. This is a particularly inconvenient solid in that there really is only one way to slice it without hitting a corner. And so you can just play the game. I mean, let's start by taking slices perpendicular to the x-axis. It looks something like that, and they go along and everything's fine right up to the point where I hit this slice, which clearly hits that corner. And that's right in the middle of my X slicing. And we don't like to slice through corners because we know what that means. We know if we slice through a corner, then in the next sort of stage of as I'm writing things down, I'm going to have to, well, then something for these values of X, I've got one story. And then for these values of X over here, I've got a different story. And I know this is going to break up into 2 separate integrals, and I don't like it. If we can possibly avoid it, we just don't like it. Okay, right? Is everybody good there? So don't do X slicing first. Likewise, don't do your Y slicing first. Look at what Y slices look like. There's a Y slice, looks fine. Here's another Y slice, doesn't look bad at all. And then, of course, there's a Y slice. We have sliced through a corner. Not good. And then our slices change. And let's see if I can draw one of these just for the perverse fun of it all. It's like this face over here is going to sort of take a cut out of our triangles. And I feel like all of a sudden a slice is going to look kind of like that. And then that, and then that. I didn't do a good job there. Slices look kind of like that. Qualitatively different story. We're in trouble. And then, by the way, the bad news doesn't end there. Of course, I also will eventually hit this corner. So that's the worst option that we have, actually, would be to put y on the outside. All of these, of course, vastly inferior to the clear choice, which would be to put z on the outside, and all my slices look qualitatively the same. They all look kind of like that. And let me do a better job of drawing that, actually. Nope, missed. Try it again. There we go. There's a reasonable Z slice. How would I slice up this Z slice? Would I slice it perpendicular to the y-axis? No, because then I would hit this corner. So that's a bad, don't put dy next, right? So we do X slicing next. X slices are all just perfectly fine little straight lines there. And then, we're in business. Okay. But you can see the artistic challenge. You can see how that's going to be. It's not that we can't do it, but it's there's a lot going on. If we were to try to do it that way, let's look instead at the projection. Let's think about let me come back up here. Is there a good projection that I could use? First, let me point out some bad projections. It would be a bad idea to try to project to the XY plane, because as you project to the XY plane, and you have, your projection kind of like this. Notice that your bottom, gosh, wrong color. Your bottom points are all on that plane, fine. But your top pieces, some of them are on that plane and some of them are on that plane. So inconsistent top surface. My upper bounds for Z are going to be bad. Right? Everybody see that? So that's a bad projection. Don't project down into the XY plane. And it's even worse. You know what? It's even worse than this, because you know what? This is not a vertical plane here. So there's actually 3 top surfaces. That's terrible. Okay, so that's right out. There is a good one though. Look at the projection over into the XZ plane. The lower bound is always on there. The upper bound is always on here. And no problem. All right, so this is a lovely projection. My projection's a triangle, dig it. My lower bound always on one surface, upper bound always on the other surface, no problem at all. And with that in mind, let's see, so this triangular this triangular projection gives me those bounds. Just have to think like a double integral, no big. Right. Lower bound always on that surface, which is where y equals 0. Upper bound always on that surface where, well, you got to solve for y, but no big deal. Solve for y, y is always that. So it just falls in your lap. Everybody happy? Okay. Alrighty. let's see, I think this is the last example. Yeah, okay. So last example, this one, I'm just going to go straight to the projection because doing this the old fashioned way, you know, the slice and dice way would have you drawing cross sections of this weird solid. By the way, this is a paraboloid with a paraboloid bit out of the middle of it, kind of, right? Right, it's a weird solid. And here's what the cross sections look like. Can I do it? First of all, my elbow is going to make it all the harder. Oh yeah.
Can we go back to the other example?
Yeah.
I'm just gonna explain, like, I got how we got the volleyball. Can you explain how we got that?
Yeah, right. So the nice thing about a projection is that once you've decided what your outside two variables are going to be, you look at the projection into that coordinate plane, and these bounds on the solid are the exact same as they would be if you're just looking in just that coordinate plane. So I just looked at this triangle, and the bounds on a triangle. Well, I mean, you do have to kind of slice it up, right? But you've got z going from 0 to 1. What did I write there? Why did I write? Okay, I think you just found a typo for me. Thank you. I'm sorry. Yeah. So this should be a 0 right there. Sorry about that. Yeah. And that was your concern?
Yeah.
Yeah. Yeah. No, that's just a typo on my part. Yeah. So that's a 0. Yeah. So 0 to 1. And then for any given value of z, x goes from, you know, there to there. And yeah, right. Okay, I'll get that fixed. Thank you for catching that. Okay. All righty. Yeah. Okay. So last example. I'm going to make a noble effort to draw a cross section on this thing, and it is not going to look good. Okay. Well. It's something kind of like this. I don't know if that's a Z slice, if you will, of this solid. So you can see why I don't want to have to take an approach that requires me to draw such things. It's really, really hard. And the harder the drawing is, the worse my picture is going to be. And the worse my picture is going to be, the worse my geometric intuition is going to be. It literally makes the problem harder. Right? Okay. So on the other hand, do I have a good projection? Absolutely. Now, don't project down into the XY plane. The projection itself doesn't look bad in the XY plane, but notice that sometimes your upper and lower bounds in the Z direction would all be on the same curve, whereas other times you'd have this weird thing happen where, you know, you're going from there to there, but then also down here, you go from sort of there to there. And so that's bad, right? They're highly inconsistent what the upper and lower surfaces are. But if we project to the XZ plane, right, the projection is a disk. The lower surface is always that paraboloid. The upper surface for the Y slices is always that paraboloid. It's not a problem. Yes.
How do you know when the problem is going to be suitable to project? So if I get it
Yeah,
here,
it's something to try. It's something to try. It's, I mean, my favorite analogy there is it's tools in a toolbox. You know, how do I know when a screwdriver is going to be more helpful than a wrench? It depends. I don't know. It's just, you know, so it's tools in your toolbox, and use whatever seems to be most useful. Here, it was just something I tried, and, you know, I'm kind of just looking at it geometrically and thinking, if I were to project this way or that way, or what if I did this, you know, and I just sort of noticed, oh yeah, look, there's a lovely projection in the Y direction. Yeah. Now, if you want to, here's another tip off, another sort of tool for your toolbox. Notice, as I've got written here, y, I would love to solve for y. So that right there suggests that y should be on the inside. That kind of begs the question, I don't know if I'm using that term correctly, of hey, maybe if x and z are going to be on the outside, I wonder if maybe there is a good projection to the xz plane. And then when you look at it more carefully, you see, oh yeah, there absolutely is. Yeah. Okay. Yeah.
I just have one more question.
Yeah.
Does it matter the order of D, C, and D dash?
In this case, it does not,
Okay.
but you know, sometimes it does. I mean, you look at this example here, it did. Right. So every question is different, and sometimes yes, sometimes no. The good news here, of course, is that the projection is a disk, and disks are symmetric in every possible way. So yeah. Okay. All right. Yeah, so it's pretty much all over once you see the projection is this. That makes the XZ bounds a double integral problem. And then the lower bound for y comes from that surface, which has y equal to that. And the upper bound for y, that point, which is on that surface. And I, again, have another typo. Sorry about that. These are Z's here. Sorry, that these should be Z's, right? Oh gosh. These are Z's. I just recopied wrong. Sorry. I'll get that fixed as well. But yeah, upper bound, this point, which is on that surface where y is equal to that. Okay. All right. Moving along. Okay, so we've got 5 minutes here to kind of get started in the change of variables section. It's a long section, by the way, one of the longest ones in the book. It's super long. Anyway, I want to kind of give you a quick alternative point of view on an old concept from Calc 1. No, I guess Calc 2. Anyway, early Calc 2, late Calc 1, called the substitution rule. Everybody remember the substitution rule? Okay, very often thought of as a kind of an algebraic trick. This is what helps you find antiderivatives when the antiderivative is hard to find. Okay. And it's very useful for that purpose. But that said, I want to reinterpret it in a totally different way. I want to think of it more kind of geometrically, if you will. I want to think of, when I make a substitution, g of t equals x, right? There's, for example, what a substitution might look like. I want to think of this g as actually being a function that actually takes you from the t-axis over to the x-axis. Let's think about that as a, there's a world over there on the left and there's a world over here on the right, and g is what moves you from left to right. Now, let's imagine that in this scenario, clean up my mess. In this scenario, imagine that there's an integral over here that I want to compute. Now, is this how we tend to use substitutions in practice in Calc 2 classes? Probably not, but don't worry about it. So imagine there is an integral that I want to compute on some interval on the x-axis. Okay. The idea is to say, well, there will be some corresponding interval over here on the t-axis where this function g sends the left endpoint of that over to here and the right endpoint of that over to this right endpoint. So in other words, there will be an interval on the left whose image is the interval over here on the right. All right, so let's figure out what that orange interval is. It's just, you just kind of have to solve for t. Okay, now I'm going to take this interval over here and I'm going to start slicing it up in the usual sort of way. So, you know, slice, 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 slice. Like that. And I make the observation that the act of slicing up this interval on the t-axis in effect slices up this interval over here on the x-axis. Now it does it in a you know, kind of a weird non-linear way, perhaps, because this g function is not, you know, this could be all kinds of weird. It could be trigonometry or polynomial or whatever. Right? So I won't get an even slicing, but nevertheless, I do get a slicing of the x-axis. And with that observed, you know, going back to, don't forget, you know, my primary interest here is to evaluate this integral. The concept of chop it up, add it up doesn't rely on the slices being the same size, right? If I take mass and chop it up into little pieces, but some of the pieces are a little smaller, some of them are a little bigger, whatever. The sum is still the mass of the whole. So irregular slicing doesn't matter. Okay, so I can think of this integral here as being sort of executed by the slices that are happening over here, like that, and I can just look at the individual components of this chop it up, add it up that I've got on this picture, and I can do what's called a pullback. The pullback says if I have an expression, if I have an expression on the right, if I were to just plug in, rewrite all the x's in terms of t's, everywhere I see an x, right? Everywhere I see an x, I just plug in, well, x is g of t. As it turns out, the punchline then is that the expression on the right can get rewritten in terms of the variable on the left. And this seems backwards, right? Because g goes to the right. G takes t values and gives you x values. G goes this way, right? But this is just how plugging in works. As if you probably never thought about it this way, but plugging in turns, if the function takes points from left to right, plugging in turns expressions from right to left. Plug in for the x's, you get stuff in terms of t's, that's right to left. So this is called a pullback. It's a fancy way of saying, yeah, plug in. Okay. There's we're one step away from sort of completing this point of view, and we're out of time. So I'll probably have to do all this over again on Monday anyway. But I wanted to plant the thought of a pullback. Y'all have a great weekend, and see you on Monday. All right. Oh yeah, and let's see now if anybody came in after. Let's see here. Okay. All right. Yeah.
I know somebody like that's what it is.